Hey guys, so tonight we're talking about laws of thermodynamics in ecosystems, which is going to be pretty important. Sounds a little boring, but we're going to go through the information pretty quickly, so stick with us. All right, so I'm going to pull up the slides really quick so you guys can follow along with your notes. In case you don't have your notes with you, I've also linked them on the bottom of this video in the description, so hopefully you guys will be good to go. All right, so you should be able to see this right now. Let's pull this up. Okay, so let's talk about laws of thermodynamics in ecosystems. So really importantly for this video, we want to talk about how the laws of thermodynamics govern the flow of energy in a system and the ability to do work. So we can think about our sun and how it feeds the earth with all of its radiant energy, but most of this energy or sunlight is not going to be taken up by our plants. It's going to be unused by organisms and lost as heat and heat of evaporation. And so there's a very, very small percentage that's actually captured in plants. And we're going to talk about how this can lead to some interesting things. So our first law is that the law of conservation is the law of conservation of energy. Now there's actually 4 laws of thermodynamics, depending on who you ask. There's the first, second, and third law, and finally a 0th law, but we're only going to talk about the first and second today. So our first law, energy in an isolated system can be transformed, but cannot be created or destroyed. So matter and energy can be converted from one form to another, but the total of the amounts of both must always remain constant. So, for example, light can be changed into heat, kinetic energy, potential energy, and whenever this conversion happens, some of that energy is given off as heat, so we lose it. And yeah, so as we look at this system right here, we have our sun and our sunlight energy being converted by the algae through photosynthesis into glucose, which is really important. And then that glucose is going to be used in cellular respiration to create our ATP, which is our cellular energy that every organism will need in all of their cells to do their life's functions. So as we go through a system, we see these conversions of energy, conversions of matter, but none of it's actually totally destroyed. Often we talk of loss of energy in a system. This is actually an energy transformation, not an energy disappearance, because we know that energy cannot be created or destroyed. All right, so the principle of conservation of energy can be modeled by the energy transformations along food chains and energy production systems. And we talked about that already just a little bit. Our second law is about entropy. So the entropy of a system increases over time. Entropy is a measure of the amount of disorder in a system. So when we talk about entropy, we talk about, for example, think about diffusion of molecules. If you spray Axe body spray in one corner of a room, it will diffuse over the entire room over a period of time. And that's an example of entropy. An increase in entropy arising from energy transformations reduces the energy available to do work. So again, we talked about heat evaporation in these different processes, and that is part of entropy as well. So we're losing a lot of energy all the time. And sometimes we just call this law how that entropy rules, or entropy increases. And this is going to be random unavailable energy that organisms can no longer use. So let's look at this diagram here. We have, for example, 1,000 joules of light energy coming from the sun to this particular plant. Unfortunately, the plant can only actually transform 10 and keep 10 joules of that energy for available food. And so we call these producers, which is a pretty okay conversion, not great. But in comparison, these 10 joules of energy are taken in by the consumer, and then that consumer only has 1 joule of energy available as food. So again, 9 joules of this energy is going to be lost to the environment. So we're losing a lot as we go on. The lion, who consumes this primary consumer here, will again only get 0.1 joules of energy from this particular organism. And as we go up, say the lion was eaten by something else, that energy would be lost as well. So if we did the math here, say this plant can only fixate about 0.2, if we're talking about the conversion of energy of the original energy source, whatever units we're using, then that next consumer is only going to get about 10% of the plant's energy. The next consumer is only going to give it 10% of that. And if we multiply it out, it turns out that the energy of the top level consumer in this food chain would only be 0.02% of the original energy source coming in. So as we go up in the food chain, or as we go up in trophic levels, we're seeing there's a huge amount of energy loss. So when we're talking about laws of thermodynamics, this is really important, and we will talk about this more as class goes on. See you guys later. All right, just kidding, I'm still on here. Yeah, so we're going to be talking about trophic levels a little bit more, and energy systems, as well as lots of other things. So stay tuned, and we'll dig deeper in a little bit. Thanks.